Modern AI models can generate award-winning artwork and write flawless sonnets, yet they frequently fail at basic deterministic math calculations. Pre-training is a form of lossy compression. Trillions of text pages are squeezed into statistical weights, capturing the shape of language rather than specific facts. This creates an intuition engine. It guesses the probable next word based on patterns, ignoring rigid calculator rules. But math and logic require strict sequential deduction. You cannot simply guess your way through a multi-hop reasoning problem. Those tasks require a machine to stop and deliberate. This creates the central challenge of modern AI engineering, finding a way to force a system designed for rapid, intuitive guessing to slow down and verify its own work. When a standard model is forced to provide a final answer immediately, it attempts to make a complex logical leap in a single, massive bound, and often it falls short. The first solution is chain of thought. We prompt the model to explicitly write out its reasoning, step by step, before it provides the final conclusion. This utilizes test-time compute. Every word the model prints acts as a physical stepping stone, buying the system the necessary time to process the next logical connection. While generating text gives the model computational space, it does not ensure the logic is sound. A model can show its work perfectly and still arrive at a nonsensical answer. In many cases, a model will mimic the structure of a brilliant proof while executing deeply flawed logic. To fix this, researchers use reinforcement learning with verifiable rewards, or RLVR. This moves the training signal away from human opinion and toward objective truth. Unlike a creative essay, a math problem provides a binary reward. A verifier, like a math checker or a code compiler, gives the model a 1 for a pass or a 0 for a fail. Through thousands of trial and error attempts, the model learns the strict rules of these verifiers. This creates a self-verification loop. It anticipates when a reasoning path leads to an error, shifting trajectory before reaching a dead end. Deterministic rewards transform the model from a word generator into its own proactive critic. However, printing out thousands of thoughts as physical text is slow and expensive. It forces the AI to speak its thoughts aloud to understand them. The final evolution is latent reasoning. Instead of building a bridge out of physical words, the model uses an internal compass. Each reasoning step shifts its internal direction, refining its path without needing to verbalize a single thought. It works like a GPS recalculating a route a dozen times a second. The model detects wrong turns in its hidden logic and silently steers its mathematical trajectory back toward the correct solution. This chart compares accuracy across 5 benchmarks. The blue hours bars represent this latent method, which consistently outperforms standard text-based chain of thought. Moving these calculations into the model's internal space improves accuracy while cutting output token usage by over 90%. Think of a novice chess player who has to physically point at the pieces and whisper every potential move out loud to see if it works. A grandmaster, by contrast, sits in silence. They calculate millions of internal permutations, evaluating and discarding strategies before ever touching a piece. They only translate that internal math into the physical world at the very end to execute this single winning move. Post-training techniques enable LLMs to pause, verify their own logic, and silently deliberate, arriving at a verified conclusion before they speak a word.